Hi guys, Mr. McIntyre here. Just wanting to finish off similar shape with similar area and similar volume. Now, before we actually go into the working and the ins and outs of using the scale factor and what impact area has on the scale factor, I want to look at this just from a basic viewpoint on the dimensions of a square. So if we take this square, and if we were to increase the dimensions of the square by a factor of 3, or we all know a scale factor of 3, then this 2 centimeters becomes 6 centimeters. And what we want to look at from there is, what does that actually impact on the area? Now, whether we times things by 3 and we call it a scale factor or not, it shouldn't really make a difference here, but it is important to have a little bit of time to consider what impact that has on the area of the shape. Naturally, it increases in length, and it's going to increase in area. So what's going to happen normally when we deal with area, we would just be looking at length times breadth, whether it's a triangle or a square. So area equals length times breadth. In this case, it's 2 times 2, and that would be 4. Okay, in this case now, we've got length times breadth, or length times length. It's 6 times 6, and that is an increase to 36. So what happens when we have increased by a scale factor of 3, we've increased the length, and the scale factor is 3. What's actually happened is we've increased the area by a scale factor of 9. What we want to look at is, what's the connection between these two numbers, 3 and 9. So the length scale factor we've got as LSF, say, that was 3. The area scale factor was 9. What happens? What can we recognize about moving from 3 to 9? Hopefully you'll pick up there that actually 9 is 3 squared, or if we were to look at it in the terms of the length scale factor, so the length scale factor squared gives us the area scale factor. So actually, the area scale factor is the length scale factor squared. And that's actually true for any calculation in this regard. So if we were to look at this example, and without going through it in this elongated version, and just look for the missing values, we can see what we would do with the working, and I'll show you that next. Okay, so if I was giving you two shapes and I told you that the length of one of these squares was 2, the area is 4 centimeters, and I then said the length of the second shape was 6 centimeters, how do I find the area? Now, we've gone through this process, but the working for this would be, we would find our corresponding sides as always, 6 and 2. So the scale factor would be new over old. I have forgotten to label them. The one with the unknown is the new, and the one with the given sides is the old. So if we have scale factor equals new over old, it's 6 over 2. So in this case, the scale factor is 3. That's the length scale factor, and that's an important thing to say. That is the length scale factor. Okay, sorry. Now, what we're going to look for now is we're going to look for the area scale factor. And we saw from the previous example, that is the length scale factor. And this time, because we're looking at area, the area scale factor dictates that it's squared, and we'll come to that for when we're looking at volume. So that means we've got 3 squared, which is 9. So for the missing area, we would look for the question mark. The question mark equals, this time, instead of multiplying by the scale factor, you multiply by the area scale factor times the missing area. In this case, the missing area is 4, so times by 4. So we have the area scale factor, which was 9, times by 4 is 36 centimeters squared. And we know that from the previous example, plus our understanding of squares, 6 times 6 is 36. Okay, we'll go through another one, although this was a kind of straightforward example, just to show you it applies elsewhere. Okay guys, example 2, we'll go through this relatively quick. This should be pretty straightforward from here. First thing you'll notice that we've got two labels, they're similar. We have a larger area that has, it tells us 60 centimeters squared. And when it comes to similar figures or similar shapes, we always want to find the scale factor, but this time we're looking at the linear scale factor, okay? Now, normally we have new over old, and that's dictated by missing values. In this case, we've only got two sets of values. I'm not sure if it's all that clear, but that's 18 centimeters on the right-hand side. So what we've got to look at is the wording here. And what it's saying here is find the smaller label, okay? So what we're wanting to do is to move from 60 to the smaller label. So in that case, what we're looking for is a reduction scale factor. So generally what that means is we want a number less than 1. So in this case, the two corresponding sides are 18 and 24. So it would make sense for us to have 18 on the top and 24 on the bottom. That's going to give us a scale factor of 18 divided by 24, which is 0.75. Now, in this instance, we're not actually looking for a side. If we had an alternate side, if we had this side here, we'd be able to calculate this side over here. But what we're looking at is area. So we need to now look at the area scale factor. Now, the area scale factor itself is just the linear scale factor squared. Okay, now that's 0.75 squared, which is 0.5625. Now, we don't necessarily need to go through that process. You could probably do that all on the calculator. So for us to calculate the small area, we take the area scale factor, we multiply it by the larger area. So we could put in 0.75 squared. We now know it's 0.5625 times by 60, and that will give us our new area, 33.75, which makes sense because we were looking for a reduction. Okay, so most important there, when we're doing the area, we're looking to find the linear scale factor first. We simply take that scale factor and square it and use that scale factor when finding the missing value. Okay, similar volume, and it may not be a surprise to you to hear me say that we're going to follow a very similar process for similar volume. We're going to use our linear scale factor. We're then going to transfer that or change that to a volume scale factor. But outside of that, there are additional elements to this question that I want to look at. So if you have a look at the question here, the diagram shows two storage jars which are mathematically similar in shape. The volume of the large jar is 1.2 litres. Now this is what I want to focus on. We see that our volume is in litres, but our lengths are in centimetres. What we need to remind ourselves of is that 1 centimetre cubed is the same as 1 milliliter. And therefore 1 litre, which is 1,000 milliliters, is the same as 1,000 centimeters cubed. And before we can tackle this type of question, and it isn't uncommon in an exam, we need to be able to change 1.2 liters to 1,200 centimeters cubed. And that means that we have both sets of units in the same format. Okay, now that we've addressed that, we now have our 1.2 litres is 1,200 centimetres cubed. We will look at the corresponding sides here. We've got an enlargement, find the volume of the smaller jar. Once again, it's a reduction, but it really won't matter if it's a reduction or an enlargement. We go through the same process, but what we do want to recognise is that the linear scale factor, in this case with the new over old, for us to make a reduction, we need it to be something that's less than 1. So in other words, we need the 24 on the top and the 30 at the bottom. So that can be simplified dividing by 6, which would give us 4 over 5 if we were to do this as a non-calculator question, or 0.8 as a calculator question. So now that we've got the linear scale factor, what we want is the volume scale factor. Okay, so the VSF, and in the past when it was area, we took the linear scale factor and we squared it, but when it's volume, we're going to cube the linear scale factor. So quite simply, we're going to take 0.8 and cube it, and that will give us our volume scale factor. Okay, what that gives us is 0.512. Okay, so now that we have the volume scale factor at 0.512, for a calculator question, what we would do is we would simply take the unknown volume, so small volume, equals the volume scale factor times by 1200 centimeters cubed. So 0.512 times 1200 centimeters cubed, which gives us 614.4 centimeters cubed. Okay, now you may have got away with doing 0.512 times 1.2 litres, in which case it would give you 0.6144 litres. So that's okay. I would always suggest keeping it the same, keeping it the same units,